A red laser beam goes from crown glass, the refraction index of n equals 1.6, to air, which has an n of 1, pretty much, with an incident angle of 0.21 radians, which is the angle of refraction in degrees. Okay, so first thing we do is we're going to draw a picture. Ooh, I'll use this shape. Go kind of like that. We'll do, yeah, that's good. And then we'll do, let's say, blue and fairly opaque. Okay, or, yeah, that's good enough. And so then we have a line that goes, laser beam, goes like this. I'm good with that. Move this down. And the idea here is we have a red laser that goes here, and then from this point, it will bend. And so, draw this real quick. I'm going to draw the direction that it bends to a little bit, right like that. Now this part up here isn't exactly true because it would bend as well when it came out. Actually, can I do that right now? Maybe. It's okay. Okay, we'll say something like that. But the only part we're interested in is right here. So there's a lot of assumptions going on in this question. So first of all, we're given a red laser beam with an index refraction of n equals 1.6 in the crown glass, which is this stuff right here. One thing to note is that when they said red laser beam, the index of refraction will change based on the color of the light or the wavelength of the light. And so what you need to keep in mind is we're assuming that this n equals 1.6 applies to this red laser beam in this question. And it's, like, well, it's kind of obvious. Otherwise, they wouldn't have given us that. But it's still an assumption we're making here. And then when they're talking about the incident angle is 0.21 radians, I'm going to assume that this incident angle is this angle right here, 0.21 radians. And it's not this angle down here. So that'd be two different things. Traditionally, it's the normal angle with relation to the normal that you're talking about when you're talking about angles of incidence. But you don't always know that, and it's good to be sure. In this case, we're not given enough information to be sure, so I'm just going to assume it's this angle right here. As a side note, if it was this angle over here and it was a bigger angle, then we'd have to be worried more about the critical angle total internal reflection. But we're not going to worry about that for this problem. So the question is, what is the angle of refraction in degrees? Okay, so this goes to Snell's law. So Snell's law is something along the lines of n1 sine of theta 1 equals n2. Oh, I'm going to run into the laser. Nope, not quite. Okay. And so n1, this will be n1, this will be n2, and n is defined as n equals c over v. And so n is the index of refraction, and it's the inverse ratio, it's the speed of light divided by the speed of the light, I guess, in the medium. So this is inversely related to speed. You could also write this as sine of theta 1 over v1 equals sine of theta 2 over v2. Now when your thought process too, they might be kind of slightly tangential. You're like, wait, I was told that speed of light is constant, and that how can light be traveling slower than the speed of light when it has to be a constant? Totally true. Extra valid question. There's a lot of nuance that's actually going on in refraction that you're not taught in this class. And for this class, you just kind of assume that light actually slows down. If you want to get a better explanation of this, check out the Feynman lectures. He goes more in depth in a more fundamental way that does a better job of explaining it. But this is kind of simplified and kind of assumed for these purposes. So we're going to go with this, that light does actually slow down. And another implication here then is this right here will be theta 2. Okay, so now getting to the question, we want to find out what the angle of refraction is in degrees. So we're trying to find theta 2. So if we look at this equation right here, whoop, I'm going to move this portion here just to free up some real estate. I don't want to get rid of it though because it's useful. It's important in life, fundamental. All right, so we're looking for theta 2. So I'm going to say that sine of theta 2 equals n1 over n2 sine of theta 1. So theta 1 is 0.21, but we're going to convert that to the calculator on clear. So we have 0.21, and there's 2 pi radians in a circle, and a circle is also 360 degrees. But since I like smaller numbers, I'm going to multiply by 180 and then divide by pi. Pi being 3.1415, more or less. So we have about 12.03 degrees. So now we're going to make sure we're in degrees. Click, click, clack, enter. Second quit. Sine of second answer, which is 12 degrees. Multiplied by n1 divided by n2. n1 is 1.6 and n2 is 1, so I'm just going to ignore that. So now we have 0.33. Now we're going to do the arc sine, inverse sine of that answer, and we get something like 19.48. Theta equals 19.4. I see a 2 in there. Looked like there was a 2. 484. Whoop. 84. Nope. That looks like a 9. 9 degrees. And one thing to notice here is another mnemonic that I use in life is that light is lazy, so it's always going to bend towards the slower medium. It's lazy, it prefers the slower medium, so it's going to bend towards the slower medium. And that's kind of the way I drew this here, was it went down this way, and then the angle, this theta 2 is actually bigger than theta 1, and that's because it's bending towards the slow medium. You might be like, what? Slower? But n1 is bigger than n2. Correct. n1 has an inverse 1 over relationship with speed. So even though n1 is bigger, 1.6 versus 1, n1 is actually slower than n2. So this red laser is going to bend towards the slower medium because it's lazy. Okay, it's not actually because it's lazy, but that's the mnemonic you use. Bend towards the slower. It's lazy. One way to visualize this is, and this is basically another mnemonic, but it's an interesting visualization, is that if you look at a thicker beam of light, something kind of like this, blum, 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 kind of like this, and it comes in like this, then this is going to be slow, this will be fast, and what happens here is it's traveling in this direction like this. Once the light exits this part right here, it goes faster. And since it's going faster, it's able to cover more distance and kind of round the corner quicker. And then once this one exits, it'll have to then, it can then go faster at that point. But since this portion of the light on the outer corner is going faster earlier, it's going to cause it to kind of rotate. If you ever played one of those like tank games when you're a kid, or maybe we still are a kid, I don't know, I'm not judging, with like the two handles, we push one forward, push one backwards, and it controls one, like either the left tread or the right tread. And if you want to turn, you then just push one tread forward and it rotates you. The idea is that one side of your tank then is going faster, which causes the whole tank to rotate. Similar concept in this mnemonic here. Since the far portion of the light exits the medium sooner, it's going to cause it to rotate because that portion will then be going faster than the portion that's still stuck in the medium. And that's kind of an understandable mnemonic to make sure you get the right direction. So to backtrack what we did real quick, we had some light. It was in a crown glass, had an index of refraction which we were given. We assumed it applied to our red laser beam. We then do our angle. The angle is generally assumed, though not always guaranteed. If you're going to use Snell's law, you have to use this angle. It's the angle between the light and the normal angle. You then look at it, then ask to find the angle of refraction, the exiting angle. And again, it's going to be with respect to the normal. And so our angle using Snell's law, such as so, is going to be 19.48. One other thing I'm going to throw out there real quick is at some point in life, you might be trying to take the arcsine of an angle that's greater than 90 degrees. Totally impossible. Your calculator will die. You're trying to find the arcsine of like, I don't know, 1.4, and like that doesn't work. Then at that point, you're going to have total internal reflection, and you need to keep in the idea that your light's internally reflected and bouncing within the medium. Think like fiber optics, that sort of thing. So I hope that helped, and I will see you next time.